Hello, we are Team 30. My name is Nathan Busak, studying mechanical engineering.
I'm Chase. I'm also studying mechanical engineering.
I'm Alex St. Peter, studying optics.
I'm Justin Rusnak, and I'm studying mechanical engineering.
I'm Ryan Stancliffe, and I'm studying electrical and computer engineering.
I'm Nathan Verdonk, and I'm studying mechanical engineering, and we're on the Brite team.
Modern flashbangs used for military or law enforcement purposes are explosive by nature and are therefore potentially harmful to not only the assailant and the user, but also to the environment in which the device is used. To mitigate the risk of unintentional harm and produce a more economic product, the development of electronic flashbangs are being investigated. Many current electronic flashbangs on the market attempt to replicate traditional flashbangs in terms of size and appearance, but may not be powerful enough to be incapacitating while remaining unharmful in the long term. Most current products have several other undesirable features. For example, they may not be rechargeable, have a limited light output in both power and effective area, may not have a noise-making capability, may not be able to be remotely detonated, and may not be rugged enough for the long-term reusability.
To fulfill the major goals Chase mentioned, the Brite needed to be reusable and a safe version of the flashbang grenade. Emitting a flashing light and loud noise, the Brite is intended to be thrown in an average lit indoor setting to disorient any assailant so that they may be apprehended in a safe and swift manner. The optical and audio output of the Brite will be safe for the assailant and the user, with no permanent harm caused while remaining unpleasant. Due to the throwable nature of the device, it will be small and rugged with the field of view of the optical output such that the target will be disoriented no matter how the device lands, as well as remotely operable.
The most important system requirement that drove our design to what it are the 6-foot drop, the non-damaging audio and optical outputs, and the 5-minute operating time requirements. To begin, we worked towards creating housing for the unit that would keep everything protected by absorbing the force from a fall. After analyzing a competitor's product, we knew balancing the audio and optical output with the battery's lifespan and being as distracting as possible would be difficult. We focused on getting close to the safety limits, then finding a battery that could do what we wanted while lasting long enough.
Moving into the mechanical design process, we completed a Q analysis matrix which helped us arrive at our point design. We began by comparing 3 different models for the Brite, which were weighed against each other in terms of estimated performance and cost vectors shown on the left. The standard cylindrical design was determined to be the best option for us to pursue, which originally had 2 LED panels on the cylindrical face, a buzzer on each end cap, and was powered by 2 9-volt batteries. After doing further research and modeling, this was changed to an LED ring that would be equally as effective no matter which side it landed on, and a much stronger LiPo battery.
We also ran a comprehensive trade study on different LEDs to compare important factors such as wavelength, current draw, optical exitance, and package size. This led us to our current LED model, which is a high-power surface mount component. Targeting a short bandwidth was important in allowing us to provide safety glasses for the user, allowing them to detain the target without being affected by the Brite by filtering out its output. As our approach to the problem, we began by purchasing a commercial flashbang and recording its audio and optical output levels. After researching safety information, such as the maximum permissible exposure from light incident on an eye and the highest non-damaging decibel level a human ear can sustain, we determined that this commercial flashbang was severely lacking. This development led us to finding LEDs and buzzers that would get as close as possible to these safety limits, as well as a battery that could power these components effectively. The Brite's high-power LEDs and 120 decibel buzzers, powered by a LiPo battery, surpasses the commercial flashbang with margin.
Anticipating the need for the Brite being able to withstand a 6-foot drop, FEAs were conducted using SolidWorks with various materials such as nylon 6.6 and aluminum. The first simulation was done using nylon 6.6 from a height of 6 and 10 feet. Both of these produced results that had a recorded maximum stress more than 3 orders of magnitude below material yield strength. When testing the model with aluminum, the results showed that around 12.37% of the model was compromised with stresses above material yield strength. We utilized the ISO clipping feature to determine exactly where these stresses occurred, which showed us that the battery box is the main issue of concern. With this knowledge, we then conducted several physical drop tests on our prototype Brite. As predicted, splintering occurred in the areas shown in the simulations. Using nylon 6.6 would have surpassed our requirement by a significant margin. This being the case, we decided to use PLA for the main housing of the device and thermoset liquid for the clear ring protecting the LEDs. These were thought to be an effective and affordable route as opposed to nylon 6.6 and polycarbonate, which would be considered if PLA and thermoset liquid proved to be inadequate. The LED protective ring was polished for maximum transparency. Soft bumpers were also included on either end to absorb the majority of the impact. Adjusting the geometry of the battery box and repeating the process led us to our current design of the Brite, which is not shown in damage thus far.
As Justin alluded to earlier, our FEA analyses showed that the Brite had potential weaknesses in the battery box that might compromise the product after a drop or throw. To mitigate this concern, we tested an initial prototype with many drops and found that there was indeed damage sustained by the battery box. To fix this, we went through approximately 8 to 10 redesigns over various components of the Brite to finally arrive at the current model, which has shown no weakness in testing. We had a strong desire to not only meet our customers' requirements, but also beat our competitors' performance. In order to do this, the team made a risky decision to use technology that no one had experience with. Specifically, we bought and tested 4 different buzzers, 3 different LED drivers, produced custom metal core PCBs, and manufactured a custom heatsink for the high-power LEDs. Because of this, the Brite exceeded all requirements in competitor performance. Battery run life is also a critical aspect of the Brite. The product needed to run long enough to be effective in any scenario, as well as be able to be used multiple times before recharging. To satisfy this requirement, we purchased and tested 4 different batteries that eventually led to the Brite far surpassing the customer's requirement.
To compile all of the results that have previously been discussed, we put together a system requirement verification matrix. It describes all of our requirements, how we test each, what limits we are referencing, the measured data we obtained, and if we pass or fail the test. The 2 pi steradian output angle is considered a pass by our sponsor, as the goal was to get as close to 100% coverage as possible, while we got up to 77%. With that in mind, all of the tests have passed.
To understand our results better, we will now go into depth for the key tests. The first test is to discuss the radio range. To pass our requirement, we needed at least 20 feet of range. As you can see from this figure, we far surpassed our requirement and we're happy with the radio performance. Now seeing this video here, you can see the Brite passing a 6-foot drop test onto concrete. The Brite functioned perfectly before and after, and there was no visible damage to the system. Following the drop test, the results from the 5-minute runtime can also be seen here. Again, we far surpassed the customer's requirements and we're happy with the performance. The next test to discuss is the optical output angle and power. From this plot, we can both meet the 2 pi steradian output angle as well as the non-damaging optical output requirements. Finally, the audio output results can be seen here. Again, we both surpassed our customer's requirement, competitor's performance, and remained non-damaging.
As for our budget, in total we have spent a little over $2,300, almost $1,700 under budget. As you can see from our purchasing list, this project required a great deal of parts. However, most of these parts were cheap. The most expensive aspect of the Brite is the LEDs. If making the Brite, one can expect to spend around $800. Due to this substantial amount of testing and little worry we would go over budget, our cost was over what someone would expect of building again. However, mass producing this product will cut costs drastically.
During the design process, many challenges common to every engineering project presented itself to the team. There were design failures, silly mistakes made, and numerous learning opportunities at every step of the project. As a team, we stood behind the knowledge we possessed as a group, expanded our understanding in areas we knew little about, and never let any setbacks stop us from completing the project. Additionally, the device meets all safety requirements and has been tested to cause no permanent damage.
The Brite team would like to thank our sponsors Matthias Whitney and Jeremy Jackson from Elliott Systems of America for providing help when needed and being flexible with system requirements. In addition, we would like to thank our mentor Mike Knopfziger for providing excellent feedback on our work and guiding us through the Form MBA course.